all to my presentation about the Nobel Prize in Physics given in 2015 to Taakaki, Kajita and Arthur B. McDonald for the discovery of neutrino oscillations. Here is the content of my presentation. At first, I will tell you why it is important to know about neutrino oscillations and will talk about neutrinos in general. Then I will introduce you the topic Cherenkov light, which is very important in both experiments. Then I will introduce you to the Nobel laureates. And the next is the solar neutrino experiment, which is actually done at Sunbury neutrino and involves, as it says, the solar neutrino. The next experiment is the supercommunicando experiment, which involves atmospheric neutrinos. And then I will bring you closer to the theory of neutrino oscillation and neutrinos. And then I will give you an outlook on the future experiment on SNO+, Sudbury Neutrino Observatory Plus, and the hypercommunicando. Neutrinos are, next to photons, the most abundant in the universe and are involved in the structural formation of the universe. So understanding the property and behavior of neutrino, in our case the neutrino oscillations, can evolve our understanding of the universe. Neutrinos interact rarely, and when they interact, it's by weak interaction or gravity. This is a reason why neutrinos can travel through Earth and the Sun, an important property which enables to measure neutrinos inside Earth for the experiment. The source of neutrinos are the Sun, particle showers in the atmosphere, nuclear reactors, and radioactive decay. Mr. Taakaki Kajita is one of the Nobel laureates. He did the experiment at supercommunicando, which was about atmospheric neutrinos, and he's a professor at the University of Tokyo, Kaisha, in Japan. Mr. Arthur B. McDonald is the second Nobel Prize laureate. He did the experiment at Sunbury Observatory, and this was about solar neutrinos. He's a professor at the Queen's University in Kingston, Canada. Now I will talk about an important topic in the experiment, namely the Cherenkov radiation. When charged particles travel faster than light in a medium, they emit Cherenkov light. The light ring tells then the velocity of the particle, and with known momentum one can determine the mass of the particle. This is what we learned in Particle Physics 1. There, in the particle detectors, we know the momentum from the silicon tracking detectors, but in the experiment another technique is used where we don't need to know the momentum. Since the pattern of light depends on the kind of charged particles, one can determine the particle by looking at the pattern of the ring. This is because the electron scatters much more than a muon, and this leads to a facial light ring for an electron. The Cherenkov ring of a muon is typically more sharp-edged. This method is used in both experiments. One experiment used water as a medium and the other used heavy matter as the medium. In the Sudbury neutrino experiment, solar neutrinos are measured. In the Sun, as you know, the proton-proton chain takes place to fuse hydrogen atoms into helium and to produce energy in the nuclear fusion. So the measured neutrinos are the 7 beryllium neutrinos. The electron neutrinos from this reaction are measured in this experiment. Introduce you the setup of the Sudbury neutrino experiment, which involved solar neutrinos. So inside the sun, electron neutrinos are produced, and those electron neutrinos travel to the detector, and when they interact with the heavy water, they can react the following ways with these 3 reactions. At first, an electron and 2 protons are produced in the charge current reaction, and in the second reaction, the neutral current reaction, a neutron, a neutrino, and a proton is produced, and in the third one, you see an elastic scattering. And you can see in this image here that in the middle there is the heavy water, which is 1,000 tons, and this costs 300 million Canadian dollars. On the outside you can see photomultipliers, which can detect the Cherenkov photons emitted by the charged particles. The Sudbury neutrino experiment consisted of 3 phases. The first one, the reactions were measured only in heavy water. The second one, in the heavy water, 2 tons of natrium chloride was added so that the neutron capture efficiency is higher than before. So one can detect more neutral current reactions than before. And in the third phase, in the heavy water, helium-3 filled neutron detectors were inserted. Those could help us distinguish the 2 reactions, namely the CC reaction and the neutral current reaction. Yes, and on the right side you see the results. So you see that the electron neutrino is only 1/3 of the total flux, since on the y-axis the ratio to the prediction of the solar model is only 0.3, and all neutrinos added, so the total flux of neutrinos comes near to the one from the prediction, the neutrino flux from the prediction. On the last slide, that the electron flux compared to the total flux is 0.3. The exact result you can see here. So it is really 1/3 of the total flux. So we see that the total neutrino flux consists of 1/3 of electron neutrinos and 2/3 of muon and tau neutrinos. Since in the sun only electron neutrinos are produced, we can really say that 2/3 of the electron neutrinos produced in the sun change their flavor into muon and tau neutrinos on their way to the detector. In the Super experiment, atmospheric neutrinos are measured. So when cosmic rays hit the atmosphere, they collide with oxygen or nitrogen, and pions, kaons, and muons are produced. And these pions and kaons and muons decay, and then mu neutrinos and electron neutrinos are produced. So I already explained to you how the atmospheric neutrinos are produced due the collision of cosmic rays with the oxygen and nitrogen in the atmosphere. And now I will explain you what happens in the detector. So when the neutrinos reach the water in the detector, muons are produced, and those muons then travel and emit faster than light and emit Cherenkov light, like explained before, and those can be detected with the photomultiplier tubes on the wall of this detector. And as you can read off here, the water volume is 50,000 tons and the detectors on the wall are 11,200. You can see here that the neutrinos are measured from all sides, so that the neutrinos can reach from below Earth to the detector or from above Earth to the detector. And on the next slide you will see the measurements. Yes, you see the results of the Super Kamiokande experiment. In the diagram, you see on the y-axis the amount of events measured, and on the x-axis you see the cosinus theta. And the theta is the finite angle, so the angle with which the flux reaches Earth, also reaches the detector. On the left side you see the electron events measured in sub-GeV or in multi-GeV, and there you see that the amount of events measured for every angle is almost the same, so there is no finite angle dependence. And on the right side you see that the muon events have a finite angle dependence, meaning that for every angle the amount of events that are measured is not the same. You see that for downgoing and upgoing muon neutrinos, there is a deficit in the upgoing muon neutrino events compared to the downgoing muon neutrino events. And to explain what is upgoing and downgoing and how you should read this plot, so the arrow you see now directed towards the detector inside the Earth is the upgoing neutrino flux, and now I will play you this animation. There you see the finite angle varying. Oh, I mentioned it wrong. So before you saw the downgoing neutrino flux, and now you see the upgoing neutrino flux. For cosinus theta 1, it was the downgoing neutrino flux, and for cosinus theta minus 1, it is the upgoing neutrino flux, so the flux you see now. Since the deficit I explained in the muon events is not visible for the electron neutrinos, since they have, as explained before, the same amounts of events on every angle, this means that the mu neutrinos change their flavor into tau neutrinos in the upgoing neutrino flux, because if they would have changed the flavor into electron neutrinos, you would have seen that in the outgoing electron flux there would have been a much higher amount of events, and that could have been explained with this deficit in the muon events. But since you don't see more events in the outgoing flux of the electron neutrino, you can say that the mu neutrinos have changed flavor into tau neutrinos in the outgoing flux. The only difference between the upgoing and the downgoing neutrino flux is that the upgoing neutrino flux crosses much more Earth than the downgoing neutrino flux. And I will explain you a fact later why this leads to the change in flavor. The effect is called MSV effect, and I will explain you this in the theory section. We will look at the exclusion of other hypotheses. So these data points are the data about the prediction, and on the y-axis you see the distance to the detector above the neutrino energy. And when you look at this, you see a sinusoidal behavior of the data above the prediction. So there are several hypotheses which could explain this, namely neutrino oscillations, neutrino decay, or neutrino decurrence. And all three are visible in the three colors. So the black is neutrino oscillations, and the red and blue are neutrino decay or neutrino decurrence. And looking at the statistics, one can say that the neutrino oscillations mostly fit the data perfectly, and the neutrino decay and neutrino decurrence doesn't seem to fit good with the data measured. So I can exclude the other hypothesis and say that this is really neutrino oscillations. Now we reach the theory part. As we know, the CKM matrix describes quark mixing. There exists also a matrix which describes neutrino mixing, namely the PMMNS matrix, the Pontecorvo Maki Nakagawa Sakata matrix. Like the flavor eigenset is a superposition of mass eigensets of quarks, explained by the CKM matrix. Analogously, the PMMNS matrix also explains the flavor violation of neutrinos. Here you see how the PMNS matrix is decomposed. This looks very similar to the CKM matrix. So the C and S in the matrix is cosinus and sinus, and the numbers there indicate which angle is meant. So for the first matrix, an angle 2, 3 is used, which can be found out in solar and reactor neutrino experiments. In the second matrix, the angle 1, 3 is used, which can be found out in atmospheric neutrino experiments. And in the third matrix, the angle 1, 2 is used, mixing angle is used, which can be found out in accelerator neutrinos experiment. And in the middle matrix you see the delta, and this is a CP violating Dirac phase. Also Majorana CP violating Majorana phases can be included in this matrix, but because we don't know if a neutrino is a Majorana particle, those are not included. Since quantum mechanics tells that change of flavor can only occur if neutrinos have mass, by proving that neutrinos oscillate also so can change flavor, we prove that neutrinos have mass with those experiments. The probability of the neutrino mixing doesn't only depend on the PMNS matrix, so the mixing angles, but also on the distance to the detector, the neutrino energy, and the squared mass difference, like the figure with several hypotheses showed. Here you see the probability formula, and you see that it is like the diagram a sinus. As you see in this diagram, that the sinus is a function of the distance to the detector L and the neutrino energy E. In the sinus is also an L and an E. Important effect which was considered in neutrino oscillations is the MSV effect, Mikhev-Smirnov-Wolfstein effect. This effect happens when neutrinos travel through matter. Thereby, the neutrino oscillations are influenced by the matter. In the case of the solar neutrino experiment, Sun had a bigger matter effect than Earth, because the Sun is more denser, so it has a higher electron density than Earth. In the case of atmospheric neutrino experiment, the Earth matter affected the oscillation. Here you see the transition probability, like before, but instead of theta we have theta m and the square difference m. This indicates the effective mixing angle and the effective squared mass difference. Below you can see what this effective square difference and effective mixing angle is. They are influenced by this x, and this x consists of the Fermi constant Gf, the neutrino energy E, and the squared mass difference delta m, and importantly Ne, the electron density. This is the factor why I said the Sun had a bigger effect on the oscillation than Earth, because this electron density is higher in the Sun than in the Earth. And when this x is equal to the cosinus 2 theta, then the transition probability gets 1 and the flavor can change. So the muon flavor can change to the tau flavor in case of atmospheric neutrinos, or the electron neutrino can change into tau or muon neutrino in the solar case. Outlook on SNO+. To observe neutrinoless double beta decay, they replace the water with tellurium nuclei in liquid scintillator. They want to replace it so they can state if neutrinos are Majorana particles or not. They want to search for invisible nucleon decay, supernova neutrinos, reactor neutrinos, and low allergy solar neutrinos. Look on hyperchromiocandie. They want to measure the CP violation, which would explain the baryon asymmetry. They want to find out about the mass hierarchy of neutrinos. Since we only know about the mass differences now, they want to detect cosmic neutrinos and detect proton decay, which is predicted by the grand unification theory. So neutrino oscillation is basically the change in flavor in a neutrino as it travels. For me, the name oscillation makes perfectly sense since this describes the sinusoidal behavior of the neutrino mixing probability. By discovering neutrino oscillations, both laboratories proved that neutrinos have mass. I hope you found this presentation interesting. Bye guys.